Hi, everybody. I'm Jason Burdick here with Engineering Tomorrow, and I would like to share with you a relatively new area of math and programming, which is being used to solve some of the most complex problems that we know. I can't wait to see what you're able to create. So, what does it mean to go viral? How does it happen? The medical term virus describes a pathogen, a small infectious agent that can spread quickly. You might not be talking about the internet, but we are using it to update our socials, order food, or even present this video today. It's a massive, complex network, but people love when their videos go viral, getting people infected emotionally, so they want to share their content. Let's watch this short video on networks that describes how something can go viral and also introduces some ways in which networks can be used to analyze bigger systems.
What does going viral on the internet really mean? And why does it happen so quickly? Why is a financial institution too big to fail? How does a virus in Africa end up in the United States in a matter of hours? Why are Facebook and Google such powerful companies at creating global connections? Well, in a word, networks. But what are networks? Everyone knows about their social network, but there are all different kinds of networks you probably haven't thought about. Networks are collections of links which combine by specific rules and behave as if they're alive. We say that networks are alive because they are in constant change. Over time, the connections within a network migrate and concentrate in new places, forming evolving structures. How the evolution and concentration of constantly changing connections occurs is the subject of a whole discipline called network theory. We can think of networks as neighborhoods. Neighborhoods are defined by maps. A Google map demonstrates the relationship between locations in exactly the same fashion a network connects hubs and nodes, using streets as links to connect neighborhoods. The reason a network can expand and evolve so quickly is based upon a mathematical concept called power functions. A power function is a mathematical amplification mechanism which over specific and very small ranges accelerates changes logarithmically. That is, a very small change in one parameter produces a huge change in another over a very specific range of values. An example of how network structure emerges is the algorithm used by Google. As the number of links around a search term, say friends, increases, connections begin to form among millions of different searches using the term friend. What Google has cleverly accomplished is a real-time mathematical model for how to predict the emergence of growing connections among billions of search terms. The algorithm Google derived collects the number of references to any search object. As references to a search object increase, the number of links also increases, creating a node. As the node increases in size, it eventually becomes a hub, which links to many nodes. Networks will continue to emerge as new ways of connecting and creating neighborhoods are defined. Perhaps you can begin to see why networks are so powerful. As Google continues to collect the billions of daily searches, new clusters of links will rapidly emerge, forming additional and growing networks. Despite the logarithmic expansion of your network, the laws of 6 degrees of separation still apply. Therefore, if you explore close friends or acquaintances in your Facebook network, everyone on average will be separated by 6 individuals or less, and the map of your social network will create neighborhoods linked by common connections among friends.
So let's break this down. What are networks? Are they just a collection of links that combine by specific rules? Are they a group of homes in your neighborhood? A group of social friends? What are they? As we begin to study networks, we'll be talking about the power function. As you noticed, as networks get larger, they become increasingly more complex. You've probably seen some power functions like x squared or x cubed. These type of functions increase rapidly with a small change in the input. First, we're going to talk about what a network is. We're going to learn a little bit more about network theory and how it can be used to model systems. Then we're going to use some tools to solve some of the most challenging problems today that are still perplexing to engineers and computer scientists, the traveling salesman problem. Using these tools we've created for you, you're going to find the fastest route a salesman can use to deliver between 9 cities. Lastly, we'll be using 2 different programming activities. One where you program a virtual drone to travel between the cities. And second, one where you use Python coding to analyze the most optimal route. As with all engineering challenges in the Engineering Tomorrow curriculum, the Networks Challenge was developed by professional engineers and engineering students. Here is our team that developed the Networks Lab. In the summer of 2023, I worked with a bunch of engineers and students to amend this Networks Challenge to include a Python coding activity and improve the way that the students were able to interact with networks. As we've discussed, a network is just a group of interconnected things. You may have heard of the internet in reference to computers, but networks can be so much more than that. From the special cells in your brain called neurons that connect everything together and give you the thought process, to the neural networks used by artificial intelligence like Amazon, Alexa, and Siri. Even FedEx and UPS are using networks to find the best way to deliver packages, which we'll be focusing on in this activity. Network theory, or the analysis of these networks, is used by engineers to make our world better. So what makes network theory so useful? How could it help in solving so many difficult problems in the engineering fields? From the US Postal Service to the pizza delivery, we all strive to find the most efficient route when traveling. As they say, time is money. Airlines use networks to make sure they get full airplane schedule with people. Google Maps and Waze try to find us the best travel routes as we navigate on these roads. There's computer, electrical, and even social networks that allow us to share what's going on in our lives. The spread of infectious disease, like the coronavirus or the flu, is being mapped every year, so we can provide better resources and opportunities along the fight for those diseases. In fact, we are looking at today's most important challenges for engineering. Here are some of them. From reverse engineering the brain, securing cyberspace, and preventing acts of terror, the internet has brought many opportunities. In 1983, the internet began as a common language for computers to communicate. As you know, this technology has grown rapidly and expanding in capacity and in speed over the last 40 years. Its development has been created by a network of engineers and scientists. Currently, this network is under attack, but cybersecurity professionals who test this network try to find ways to stop the spread of malware and viruses. There's also the war of terror and other wars that are constantly attacking this network as people try to acquire materials which can cause harm. Your first goal here in part 2 is to introduce you to the famous traveling salesman problem. This problem is a great way to introduce you to network analysis with the question, how do we find the shortest path as a bird could fly between all the cities to visit them one time and return back to the starting point? Let's say you have to schedule an airplane. Well, you want the most amount of people to fit on that airliner. Let's say you want to shorten delivery times, minimize delivery costs, save fuel, and maybe even help save the world. Well, this is an example of a network problem being applied. Companies like FedEx, UPS, and Amazon. This also scales to a local delivery driver who drives around town for DoorDash or Grubhub. The Network Challenge will give you an introduction to the traveling salesman problem in part 1. And in part 2, you will use this information to find the optimized route. What do you think? Does it matter where we start for the problem? In this online simulator, you will be guided to try to find the optimal path between a set number of cities. You will challenge students in the class to see who can find the shortest path. As you can see here in the simulation, the path here shown above is not the optimal path. Your goal will be to find the shortest route between all the cities. As we increase the number of cities, this path will become more and more challenging. You'll be recording in your student workbook both the optimal distance, your distance, and the difference between those two distances. Ask your fellow students and see what they find. All right, welcome to the simulation for the traveling salesman problem. This will help us simulate and try to play with, give us more experience in how these ideas work. If you're more interested in how the algorithms work, you can try this tab at the top, description of the algorithms. And at the end, it'll give us the optimal tour, the optimal path between in the simulation. So here we're going to start with playing the game. You can go change the number of cities. This will be the student workbook, how you want to change between them. I'm going to start here with 13. And you can also look at how it explores the different distances between Euclidean, which is like the Pythagorean theorem, or different metrics between how it calculates the distance. Let's start the game. Here we have our 13 cities. Your goal here is to start wherever you choose to and navigate your way between these cities. I'm just going to quickly show this, and we can fast forward in the video. Now that we've connected up our cities, or we think we found our optimal path, we can show the solution. When you show the solution, it will pause the game and not let you change anything. With the change tab. Unfortunately, our tour was not optimal. As you can see here, the optimal path of 24,000 and our path of 27,000 kilometers. It was too bad. We didn't find the optimal path. The optimal path here is shown in dark blue lines with a calculated time of 11 milliseconds, much better than the algorithm that we're going to show you later on. Work against other students and see who can find the optimal route. Here in part 3, we'll begin solving the traveling salesman problem using a couple tools. As we discussed, when we hear the word network, all sorts of things start springing to our mind, like social networks or the internet. But the power of network theory is the high degree or adaptability that can be applied to so many different types of problems. This language of networks is called graph theory. And it's the formal language of mathematics that talks about how these networks are built and adjust. The first theory of graphs goes back to the 18th century mathematician Euler. And the first textbook came around 1958, but most of the work in the field has happened in the last few decades. In essence, a graph consists of just two parts, a vertice and an edge. A vertice is just a node or a thing, something we can ascribe value to it. It could be a person, a car, a planet, a farm, a city, or even a molecule. In this case of the traveling salesman, vertices are cities that we will visit. Edges can be defined as the relationship between those nodes. This connection may be tangible, like a cable in a computer network, or roads between cities, or maybe something intangible, like a social relationship or friendship. Using this model, the traveling salesman problem becomes a minimization issue, where the salesman starts and finishes the same city, and we try to reduce the path or distance between them. Let's look at the route above between cities A, B, C, and D. Can you find the shortest path? As you can see, the path between A and B and C and D look like the shortest paths of 20 and 12. What's the next shortest? The path between B and C. Using this path between A to B to C to D, you can navigate the shortest route. Well, this was probably easy with 4 cities. How many paths do you think there are? So how do we solve the traveling salesman problem without a simulator, like we used in step 1? As the number of cities goes up, the number of possible paths goes up very, very quickly. Let's look at this map. How can we navigate between a few cities? What if we only have 3? With 3 cities, there's only one path between them, if we don't care about which direction we go. With 4 cities, we now have 3 different sequences or 3 paths that we can use to travel. And with 5 cities, the number of paths becomes 12. This type of scaling is a factorial type mathematical operation, which is shown up here as n minus 1 factorial over 2. They're divided by 2 because we don't care which way we go around the cities. And as we increase the number of cities, this math becomes very, very complex, with 12 cities in the millions of possible paths. And this problem becomes very, very difficult to solve by a computer even. As the number of cities increases, the number of operations that need to be performed becomes huge. This type of problem is called NP-hard. Researchers still don't know if this problem has a solution in the complexity of low enough complexity in the orange region below. The traveling salesman problem is one of the most studied problems in computational mathematics, and yet still no effective solution has been found. A solution for this general case would earn you $1 million prize from the Clay Mathematics Institute. Are you interested now? To solve the traveling salesman problem in practice, heuristics are used, or shortcuts, that lets us reduce the complexity of the problem. But this sometimes results in suboptimal paths. But don't worry. For this part of the breakout, we'll only be working with 9 cities. You will try to find the shortest trip between the 9 cities on this map. Using the spreadsheet we've created for you, you will look at the map and type in the X and Y coordinates for each of them. As you enter the coordinates, the spreadsheet will automatically calculate distances between the city and will put a value for the total distance of the path. It'll help you save some time. As you input those distances, the total distance between the cities will be calculated in this matrix table below. Remember, you should only visit each city once. The cities along the diagonal have a distance of 0, because the distance from Seattle to Seattle is 0, or LA to LA is 0. You'll begin recording these paths in your student workbook, as well as the total distance that you solve. Let's go look at the spreadsheet. Welcome to the spreadsheet that'll help us calculate the distances between our 9 cities. The first thing you'll have to do is map the distance using the XY axes here on the side. The first city, LA, you'll notice has a distance of 1.5 in the X direction and 7 in the Y direction. I'm going to speed this up as I enter a few cities. I don't want to solve all the cities for you, so I'll leave it there. But as we enter the cities into our data table, the routes become solved in our matrix here. You'll notice the distance of 0 between Seattle and Seattle, whereas the distance in Seattle to LA is 896, or Seattle to LA over here is also 896 miles. All this math is being calculated, as you notice, because we're not using miles on this graph here. So we're using a multiplier to change between one and the other. Finally, we're going to try and connect those cities. And since we currently have 3, we're going to go from Seattle to Denver to LA. So A to C to B. And as we do that, you can see our map becomes connected over here. As you enter all your cities and map your distance, it will calculate the total distance. I'm just going to put all B here for the rest. After you've chosen all of your cities, and again, I'm cheating here because I'm not visiting all of my cities, it will calculate the total distance for you, which is here 2,724 miles, and a total cost of $681 for that, approximately, for that gas. Try to find the optimal route and compete against other students in the class. When you're done, you'll move on to sheet 2 and copy out the data from this chart, and that'll be used for the Python simulation if you choose to do so in part 3. As the final part of this challenge, you'll be able to pick the activity you want to work on. First, there'll be coding a virtual drone. Having no coding experience, we'll use an MBlock or Scratch similar coding language to introduce you to the coding process, and you'll be able to challenge other students in class to see who can create the shortest path and the quickest route. The next opportunity will be using Python. If you have any coding experience before, or you're interested in how Python or the traveling salesman problem might work, this is a great opportunity for you. You will not have to write any Python code, but you will have to change or modify a few sections to solve the challenge. Now that you have the path to the traveling salesman problem, it's time for you to program your drone to fly that path. A drone is an unmanned aerial vehicle, essentially a flying robot that can be remotely controlled or fly autonomously using software, GPS, and other sensors. We will be using MBlock, which is similar to a Scratch-based virtual language. To solve this challenge, you will guide your drone between the cities as shown in this map. Be sure to try to find the most optimal route. In part 5, we're getting into a little Python programming, which is another option for today's challenge that lets you explore how a computer program using Python can help find the shortest path between the 9 cities shown above. In this section, we will be using Google Colab Workbook as an IDE to help guide you through the solution to this problem. We will show you some best practices that computer programmers use when designing code and some techniques used in solving this problem. Explore the Colab as it's like a playground. Don't worry about breaking anything, just try things out. If anything breaks, you'll be able to refresh the page. If you'd like to make your own copy, we'll show you how to do that as well so you can save the changes that you make. You'll have a chance to modify and make adjustments to the code and see how programmers write code to become efficient and choose documentation so that others can work on the same challenge. Finally, there'll be a further extension that tries to optimize the solution. Now we're in Google Colab's Workbook, or IDE, Integrated Development Environment. Feel free to treat this as a playground and play around. If you break anything, you can always just refresh the page and it'll go back to the original version. If you'd like to save a copy, you can go up into File and save a copy to your Drive or GitHub, whatever you choose. All the sections in green are comments. So those are actually not coding sections. Those are just part for you to review and to learn about how Python works. And the parts you can change have no hashtag at the beginning and are in black, red, or usually blue. So I'm going to go here and input a name here or change the math here. You can run each section here by pushing the play button, and that cell will run. And it should change the output here in the bottom. As you run the cells below, they will input data for the next part of the program that's running. Between each section of the code is some documentation that'll explain what's going on in the algorithm. It might help you understand what's about to happen in the code and give you a better idea of how to optimize the solution. Before we start anything, we'll have to copy paste that data into our cities.txt file by clicking over here on the left and creating a text file. All this is shown in the workbook. When you get to each section, you can press the play button and run that section. Below each section will be an output for the number of cities you have or the distances or locations of those cities. So in section 0, we import all of our cities and where we think the distances are that you calculated. In section 1, we will generate all the paths between those 9 cities. So using the permutation tools in Python, we'll create all the possible permutations and all the possible paths. This is calculated very quickly. In part 2, we'll use the distance function to calculate the distances of each of the paths. In part 3, we'll put it all together and see how the distance of all those paths can be optimized. At the bottom of part 3, you'll see the number of unique paths using 9 cities and how long it took our simulation to run. Well, as you enter more and more cities, our algorithm becomes a lot more complex, and this can be seen in the next section. Here's all the paths that were created, and of course the most optimal path is down here with a distance of less than 4,000. Lastly, if you love working in Python and want to learn more about finding the optimal solution, the final extension coding activity at the bottom will take you through some different applications and get you actually using some Python code to find the optimal solution. Here's a flowchart of each section in the Google Colab. It's a visual representation that might help guide you through the complexity of the problem. It allows you to break down this complex issue into smaller, more digestible parts. You will see that in these sections, we will first build the cities, then we will build all the paths, then we will, inside the final section, compute the distance of the various paths. 2 important points to remember. You'll need to import your data from the spreadsheet into the simulation, which will be shown in the student workbook. You'll then need to modify certain sections of the code to try and find the optimal solution. Don't worry, you can't break anything. If you found some of today's work interesting, you may be interested in other topics like artificial intelligence, data science, applied mathematics, neural mapping of the brain, and others. If you like the coding activity, there's lots of things you can get into, like operations research, computer science, systems engineering, and many others. I come from a background in industrial engineering, but there's many techniques and problems that need to be solved using these ideas. Thank you so much for your attention, and hope you've enjoyed learning some new skills and tools.